Welcome to day 11. Over the past 2 weeks, we've covered AI theory and applications. We've explored how generative models work, seen AI transform healthcare and autonomous systems. But there's a massive gap between research prototypes and production systems. Today, we bridge that gap. Production ML is where most AI practitioners work. It's less glamorous than research, but absolutely critical. Most AI value comes from successfully deployed systems, not novel algorithms. Today, we explore building systems that work reliably at scale. We'll cover end to end ML pipelines from data collection through monitoring. We'll discuss data engineering, how to build reliable data infrastructure, feature engineering, extracting signals from raw data, model training at scale, managing compute and experiments, model serving, making predictions available to applications, monitoring, detecting when systems degrade, MLOps, automating these processes. By the end of today, you'll understand the full systems engineering required for production AI. You'll see why infrastructure and engineering matter as much as algorithms. You'll appreciate the complexity of deployed systems. This knowledge is crucial whether you're building systems at startups or enterprises. Let's explore production AI. Here's exactly what we'll accomplish today in production machine learning. First, we'll understand end-to-end pipelines. How does data flow from collection through deployment? What's the architecture? What components do you need? Second, we'll explore data engineering. Most ML work is data related. Collecting reliable data, storing it efficiently, processing it consistently. This is unglamorous but essential. Third, feature engineering, extracting useful signals from raw data. Good features enable better models than fancy algorithms on bad features. Fourth, we'll master model training at scale. How do you train on billion-row data sets? How do you manage experiments? How do you track what worked? Fifth, model serving, making predictions available to applications. Should you use batch predictions or real-time APIs? How do you handle latency, scale to millions of predictions per second? Sixth, monitoring, detecting when model performance degrades. Models decay over time as data distribution shift. Without monitoring, degradation goes unnoticed. Finally, we'll discuss MLOps, automating these processes. Manual processes don't scale. You need automation for data pipelines, training, serving, monitoring. After today, you'll understand production ML is a systems engineering discipline. Understanding the full pipeline is crucial for production systems. Each stage matters. Data collection gathers raw data from diverse sources. User interactions, sensors, databases, APIs. Data quality depends on careful collection. Errors here propagate through the pipeline. Data storage requires reliable infrastructure. Data must be accessible for processing. Storage must be scalable. Systems grow from terabytes to petabytes. Backup and redundancy prevent data loss. Data processing cleans and validates. Remove duplicates, handle missing values, detect outliers, validate formats. Bad data produces bad models. Processing must be reproducible and auditable. Feature engineering extracts useful signals. Raw features are often not directly useful. Engineers create features capturing domain knowledge, temporal patterns, interactions, transformations. Feature engineering is where domain expertise and creativity matter most. Model training learns from processed data. At scale, you have billions of examples. Training requires distributed computing. Hyperparameter tuning, regularization, optimization all matter. Model evaluation assesses rigorously. Test on held out data reflecting production distribution. Evaluate multiple metrics appropriate for use case. Model deployment makes predictions available. Batch processing for non-time sensitive tasks. Real-time APIs for low latency requirements. Edge deployment for on-device inference. Monitoring detects when model performance degrades. Retrain when needed. This pipeline is continuous, not one time but iterative. Data engineering is foundational. Without reliable data infrastructure, ML fails. Data engineers build systems collecting, storing, and processing data at scale. Data collection systems ingest data reliably. Data comes from diverse sources with different formats and frequencies. Collection systems must handle failures, duplicates, late arrivals. They must be scalable and cost efficient. Modern systems use message queues like Kafka for reliability. Data warehousing provides centralized storage. Raw data is valuable but messy. Warehouses store cleaned, organized data enabling analytics and ML. Schemas define structure. Partitioning enables efficient querying. Warehouses like Snowflake, BigQuery scale to petabytes. ETL, extract, transform, load, pipelines process data. Extract from sources, transform into useful formats, load into warehouses. Modern systems use ELT, extract, load, transform. Load first, transform later for flexibility. Orchestration tools like Airflow manage complex pipelines with dependencies. Data validation ensures quality. Check completeness, accuracy, consistency. Detect missing values, outliers, schema violations. Validation catches problems early before they reach models. Data versioning tracks changes. Datasets evolve. Versioning enables reproducing experiments with specific data versions. Most ML work is data related. Getting data infrastructure right is critical for success. Features determine model capability more than algorithms. Good features enable simple models to perform well. Bad features require complex models compensating for poor signal. Raw features are directly available: user age, product price, transaction amount. Often, raw features aren't directly useful. You need to transform them. Engineered features are created from raw data. Examples: log transformation of prices, many products cheap, few expensive. Binning age into ranges. Time since last purchase captures recency. Domain knowledge is crucial. Experts understand which features matter. A fraud expert knows transaction velocity, how many transactions quickly, indicates fraud. An NLP expert knows character level features sometimes outperform word level features. Incorporating domain knowledge into features is more valuable than hoping algorithms discover it. Temporal features capture time patterns: day of week, hour of day, seasonality. Cyclical encoding represents cyclical time. Recent history versus distant history often have different predictive power. Lag features, previous values, capture dependencies. Interaction features capture relationships. Product category and user age together might predict preference better than either alone. Polynomial features capture nonlinearity. Cross features across categorical variables capture complex dependencies. Feature selection chooses most useful features. Too many features cause overfitting. Slow training hurt interpretability. Statistical tests, model-based importance, domain knowledge all inform selection. The best models often use feature engineered rather than raw data. Training at scale requires engineering beyond single machine ML. Distributed training parallelizes across multiple machines. Modern datasets are enormous. GPT-3 trained on hundreds of terabytes of text. You need distributed systems. Data parallelism splits data across machines. Each machine processes its partition, computes gradients, aggregates updates. Parameter servers coordinate. Modern frameworks like PyTorch and TensorFlow handle this. Hyperparameter tuning optimizes parameters controlling learning. Learning rate, batch size, regularization, architecture choices. Grid search tries all combinations. Expensive. Random search surprisingly effective. Bayesian optimization learns which parameters matter. Tools like Optuna automate tuning, experiment tracking records what you tried and results. Tried learning rate 0.001, accuracy 0.92. Tried 0.01, accuracy 0.93. You need systematic tracking. Tools like MLflow record parameters, metrics, artifacts. This enables reproducibility and analysis of what worked. Validation strategies assess realistic performance. Train test split is basic. Cross-validation uses multiple train test splits, averages results. For time series, temporal cross-validation respects chronological order. Train on past, test on future. Wrong validation leads to over-optimistic results. Training infrastructure is crucial. GPUs accelerate computation dramatically. Cloud platforms like AWS, GCP, Azure provide training services. Kubernetes orchestrates complex jobs. Investment in training infrastructure pays dividends through faster iteration. Model evaluation is crucial but often done poorly. Accuracy is misleading, especially for imbalanced data. Accuracy, percentage of correct predictions. If 99% of data is negative, a model always predicting negative gets 99% accuracy but is useless. Accuracy hides failures in minority class. Precision and recall distinguish different errors. Precision of positive predictions, how many are correct. High precision ensures few false alarms. Recall of actual positives, how many did you catch? High recall count few misses. Trade off between them. Fraud detection wants high precision, false alarms are expensive. Medical screening wants high recall, missing cases is costly. AUC row C, area under the receiver operating characteristic curve, evaluates performance across different thresholds, useful for imbalanced data. F1 score balances precision and recall. Business metrics matter most. Ultimately, does the model improve business outcomes, revenue, user engagement, cost reduction? Technical metrics don't guarantee business value, always connect to business impact. Offline evaluation uses test data, but test data might not reflect production distribution. Online evaluation tests live on real users. A/B testing compares new model to baseline. Gradual rollout identifies problems early. Online evaluation is reality. Optimizing offline metrics that don't translate to online performance is wasted effort. Deploying models requires serving predictions efficiently. Different use cases have different requirements. Batch serving processes data periodically. Run predictions on all records nightly. Results stored for next day use. Good for non-urgent tasks. Email recommendations, batch fraud detection. Efficient but not real time. Real-time serving requires low latency. User asks for a recommendation, expects response in milliseconds. This requires online prediction services, models loaded in memory, requests processed immediately. Harder than batch but necessary for interactive applications. Model APIs make predictions accessible to applications. REST APIs enable easy integration. Request with features, receive prediction. Cloud platforms provide managed services handling scaling. TensorFlow serving, Kserve, Seldon standardize this. Model versioning tracks multiple versions. Models improve over time. You need ability to roll back if new version performs poorly. Maintain previous versions. Gradually migrate traffic to new versions. Canary deployments test new models on small percentage of traffic first. Containerization with Docker ensures reproducibility. Package model with dependencies. Container runs identically everywhere. Kubernetes orchestrates containers at scale. Traditional servers are replaced by containerized microservices. Models degrade in production. Without monitoring, degradation goes unnoticed, causing harm. Monitoring is essential. Performance monitoring tracks model metrics: accuracy, precision, recall, business metrics. Plotted over time. Visualization reveals trends. Sudden drops indicate problems. Gradual decay indicates concept drift. Data drift, input distribution changes. Users change behavior. Seasonality patterns shift. Model trained on old distribution performs poorly on new data. Detecting data drift enables proactive retraining. Concept drift, relationship between inputs and outputs changes. Fraud patterns evolve as criminals adapt. Market dynamics change. What predicted well before doesn't predict now. Concept drift is harder to detect than data drift because you don't know ground truth immediately. Alerts notify teams of problems. If accuracy drops below threshold, alert. If prediction latency exceeds limit, alert. Automated alerts enable rapid response. Manual monitoring doesn't scale. Retraining refreshes models. When performance degrades, collect new data and retrain. Some systems retrain continuously. Weekly retraining ensures fresh models. Automated retraining pipelines update models without manual intervention. Monitoring creates a feedback loop. Collect predictions, collect true labels, measure performance, retrain if needed. This loop is essential for maintaining performance over time. Models without monitoring suffer silent failures. MLOps applies software engineering best practices to ML. Manual processes don't scale. Automation is essential. CI/CD, continuous integration, continuous deployment, for ML automates testing and deployment. Code changes trigger automated testing. Models pass tests before deploying. Deployments are frequent and safe. This reduces time from idea to production. Orchestration manages complex workflows. Data pipelines have dependencies. Some steps wait for others. Workflow engines like Airflow, DAGs, Kubeflow schedule and monitor jobs. Failures trigger alerts or retries. Complex pipelines with thousands of jobs are managed reliably. Infrastructure as code defines infrastructure in configuration files. Deployments are reproducible. Spin up exact same infrastructure in different regions or clouds. Version control infrastructure changes like code. Enables reproducibility and disaster recovery. Experiment tracking records all experiments systematically. Model versions, parameters, metrics, artifacts, enables reproducing experiments, comparison across experiments informs decisions. Tools like MLflow make this standard practice. Governance tracks model provenance. Who trained this model? What data? What code? When deployed? This is crucial for compliance, debugging, understanding system behavior. Organizations track data lineage, model lineage, enabling audits and traceability. Feature stores centralize feature management across ML systems, critical for production ML. Without feature stores, teams define features in training scripts, serving code, data pipelines separately. Inconsistencies emerge. Feature A computed one way in training, another way in serving, results in training serving skew. Model works great in training, fails in production. This is a real and common problem. Feature stores provide single source of truth for features. Define each feature once. Compute it centrally. Training and serving use the same feature computation. Consistency guaranteed. Features reused across multiple models and teams. Reduces redundancy. Online versus offline features. Training needs historical features efficiently, batch operations. Serving needs low latency feature retrieval. Real-time requirement. Feature stores have both. Offline store for batch jobs. Online store, in-memory cache for real-time serving. Background job keeps them synchronized. Feature discovery. Feature stores catalog available features. What features exist? What do they compute? How fresh are they? Documentation enables discovery and reuse. Teams avoid duplicating work. Popular feature stores include Tecton, Feast, Hopsworks. They're becoming standard infrastructure for production ML teams. Investment in feature store infrastructure pays dividends through consistency and rapid experimentation. A/B testing validates that improvements actually help. Not all improvements improve business metrics. A/B testing measures real-world impact. A/B tests compare control, baseline versus treatment, new model. Users randomly assigned to each. Metrics tracked. If treatment is better, deploy it. Otherwise, keep control or iterate. Randomization ensures fairness. Without randomization, systematic differences between groups bias results. Random assignment creates comparable groups. Statistical analysis determines significance. Is difference real or random chance? With large sample sizes, even tiny differences are significant. With small samples, big differences might be flukes. Statistical power calculation determines sample size needed. Business metrics matter. New model improves technical metrics but hurts engagement or revenue, not worth deploying. Track business impact, cost, revenue, engagement, retention, user satisfaction. These matter more than accuracy. Velocity versus rigor trade-off. Thorough experiments take time. Quick experiments sacrifice power. Optimal balance depends on context. High-stakes decisions need rigor. Exploratory experiments can be quicker. Organizations develop cultures enabling rapid, safe experimentation. Multiple simultaneous tests accelerate learning. Data quality is foundation for ML. Garbage in, garbage out. Poor data quality leads to poor models and poor decisions. Schema validation checks data matches expected format. Columns exist, types are correct, ranges are valid, catches upstream errors early. Schema changes are detected. Completeness ensures sufficient data. Missing values are inevitable, but too many missing values indicate problems. Thresholds detect when missingness is excessive. Some columns always have values, others missing 50%. Investigate why. Accuracy. Does data reflect reality? Prices should be positive, dates reasonable, user IDs valid. Statistical distributions should match expectations. Outliers warrant investigation. Are they errors or legitimate extremes? Consistency. Same entity represented consistently. User ID 1.345 shouldn't have conflicting addresses. Products shouldn't have multiple IDs. Inconsistencies indicate errors. Deduplication and normalization ensure consistency. Timeliness. Data is recent. For real-time systems, staleness is unacceptable. For batch systems, day-old data might be fine, but multi-month-old data is problematic. Data quality issues compound. Errors in raw data propagate through pipelines. Fixing downstream is expensive. Catching problems early through validation is essential. Automated validation catches issues before they reach models. Modern ML requires significant compute. Understanding infrastructure is crucial for productive work at scale. GPUs accelerate neural network training 10 to 100x over CPUs. Parallel matrix operations run extremely fast on GPUs. TPUs, tensor processing units, are even more specialized. GPUs are expensive but necessary for practical deep learning. Distributed systems scale beyond single machines. Data too large to fit in one machine's memory, training too slow on one machine. Distributed systems spread computation. Challenges: network communication, fault tolerance, debugging, but essential for large-scale ML. Cloud platforms provide on-demand compute, rent GPUs by the hour, scale up for big jobs, scale down when done, pay for what you use. Major platforms: AWS, most features; GCP, good ML integration; Azure, good for enterprises. Reduces capital expenditure, enables flexibility. Kubernetes orchestrates containerized workloads, schedule containers on machines. Handle failures by restarting. Scale workloads up, down based on demand. Complex but essential for operating ML systems at scale. Cost optimization is important. Compute is expensive. Efficient GPU usage saves money. Choosing right machine type. Spot instances. Discounted but can be interrupted. Autoscaling. Only use what you need. Monitoring costs prevents surprises. Large teams require serious infrastructure investment. Tomorrow is day 12, AI teams and career paths. We shift from technical systems to organizational and career dimensions. Today, we've explored production ML, the engineering required for deployed systems. Tomorrow, we'll explore how these systems are built. Who builds them? What roles exist? How do teams organize? What career paths exist in AI? We'll explore ML engineer roles, building and maintaining production systems. Data scientists, exploring data and developing models. Data engineers, building data infrastructure. ML researchers, exploring novel techniques. ML product managers, guiding development. Each role has different skills and career trajectories. We'll discuss how teams organize and collaborate. Cross-functional teams combining diverse expertise. Challenges in communication between specialized roles. How different roles contribute to successful AI systems. We'll explore career paths, from junior engineer to senior architect, from specialist to generalist. Industry versus research, startup versus enterprise, building skills and expertise over time. Excellent work today. You now understand production ML systems, the engineering required for deployed AI. You appreciate data, features, training, serving, monitoring. You understand MLOps automating workflows. This knowledge is crucial for real-world AI work. See you tomorrow as we explore AI careers and team dynamics.